All right, Mark, I will let people in as they join, but I think we'll get started. So as a reminder, I have this slide up here that you can see. If you're not familiar with Ambient, if you're not one of our employees and you're somebody joining us as a guest, Ambient is a collection of HVAC design companies across the East region. And we have a number of different HVAC companies within our portfolio. And I encourage you to check us out at ambient-enterprises.com. For this call, if you'd like to participate, ask questions, we always suggest you have your camera on, although it's not required. You can mute and unmute your microphone throughout the class, so just make sure that when Mark is presenting, you have yourself muted, and if you have any questions later on, you can go ahead and unmute yourself. And then and I could see that most people have done it already. If you join the call, just make sure you're using the same name that you did when you registered, just to make sure that we get the PDH credit issued to you. That will most likely take a couple of weeks, but of course you can always follow up with us if you have any questions. And without further ado, we have Mark W. Fly, the esteemed Mark Fly, with us from Aaon Inc. And he's going to take it over from here. And I hope you guys enjoy, and thanks again for joining. So Mark, let me pass this over to you. And
okay, let me get my screen on here.
Excellent. All right, Mark, take it away.
Okay, so good afternoon, or it's still morning for me because I'm in Tulsa, Oklahoma, but we're moving along here a little bit. I'm Mark Fly. I am my grandiose title right now for Aaon is the executive director of the Norman Asbjornson Innovation Center, which is our laboratory. That was my pre-retirement job. My pre-retirement job currently really is more along the lines of running around being an ASHRAE distinguished lecturer and doing things like this for some of our representatives and people associated with Aaon. So I've had a lot of roles at Aaon. I came into Aaon in 2006 as the director of engineering, and that kind of evolved into I was also did a lot of government affairs and regulatory stuff. So a lot of the things I'm going to talk about is kind of things that I've been involved in as far as HRI and ASHRAE and DOE rulemaking. And being an engineer, I always like to understand where everything comes from. So part of this is really a history lesson on how the sausage gets made. But so our learning objectives today basically are talking about certified rating programs, where they come from, what are the different metrics for full load and part load. I'm going to talk a little bit about what's coming up in the next few years and some things that just happened recently. We're going to talk a little bit about what the testing means and where the testing points and ratings are and what can you do with them and what can't you do with them. And kind of finish up with talking about, how these ratings affect energy consumptions, real energy consumptions, and building performance. So just getting started, this is an acronym fest to a certain extent. So there's lots of players in this. So kind of starting out from the beginning, ASHRAE, used to be called the American Society of Heating, Refrigeration, and Air Conditioning Engineers. I've been involved in them since the 80s, and have actually been on their board of directors at one point in time. But they developed the method of test. So they develop how units are tested. And the important thing about ASHRAE to understand is that the ASHRAE standards are truly consensus standards. They're developed under the ANSI ISO consensus standard process, which means that there are representatives involved in this from all aspects of the building industry: contractors, owners, consulting engineers, manufacturers. Everybody's involved in this. it can be a long and drawn out process. Sometimes we call it moving at the speed of ASHRAE, and that's not a compliment. But it's important to understand that these are publicly reviewed standards that represent the consensus of the industry. So, so the ASHRAE is probably the purest form of actually putting standards together. And so what ASHRAE does is tell you, how do you test a piece of equipment? What conditions do you test it in? What kind of facilities? What kind of tolerances and what kind of measurements do you have to make? The next player that kind of enters this in the U.S. is HRI. HRI is the Air Conditioning, Heating, and Refrigeration Institute in the U.S. and even though ASHRAE and HRI like to say they're worldwide, and they are to a certain extent, they are certainly more prominent in North America. But HRI develops listing standards, and so for like unitary products, we've been listing products in HRI for over 60 years. So they developed they developed the ratings, and they have a MOU, or a memorandum of understanding, with ASHRAE. So whenever ASHRAE standards are developed and HRI listing standards are developed, they're done as a joint venture between the two groups. And HRI is about 300 manufacturers. They represent about 90% of commercial air conditioning manufacturing. So basically, these two work together. The two primarily listing standards that you're going to see for unitary equipment is HRI 210, 240 and HRI 340, 360. So actually, those used to be 4 standards. I don't know why we didn't drop the number, but that's what they are. And so 210, 240 is for any equipment under 5 tons, and generally is dominated by residential. And then anything over 5 tons, which is dominated by commercial products, is under 340, 360. Both of those standards are based on the ASHRAE ANSI standard 37, which is the method of test. So basically, how do I test electrically driven unitary air conditioning equipment? So enter the next player is the U.S. Department of Energy. The U.S. Department of Energy has had the authority to regulate efficiency of HVAC equipment since the Energy Policy and Conservation Act of 1975, EPAC, or sometimes you hear it pronounced EPCA. So since 1975, they've had the authority to regulate them. They didn't actually regulate unitary air conditioning equipment till 2013. They were too busy taking out incandescent light bulbs, regulating refrigerators and dishwashers, and all those other things that fall under EPAC. So EPAC, when the Department of Energy was started in 1975 under Jimmy Carter, a law was passed. It's been amended a few times. It has not actually been rewritten. And in my personal opinion, it really needs to be rewritten because there's some issues with it. But so in 2013, a negotiated rulemaking was convened by U.S. Department of Energy, and I'll talk a little bit more about how that process works. But under the Federal Rulemaking and Advisory Committee for Appliances, ASRAC, and we all sat together in the room, and I was involved in this back in 2013. So like I said, I've been involved in ASHRAE since 1982. I've chaired 9.1. I just rolled off as chair of 9.1 and have been a member since 1990. That's Large Building Systems, which talks about all kinds of different building systems. I was on the ASHRAE board of directors through 2017, rolling off. And I chaired the Certified HVAC Designer certification. So I've done a bunch of different things in ASHRAE and still involved and continue to do that. I've been involved in HRI since I joined. I was involved a little bit before I joined Aaon, but I've been really involved since I joined Aaon in 2006. I was on their board of directors from 13 to 17. I chaired the unitary large air conditioning section, which is that equipment bigger than 5 tons. I've been on this, what we call the system steering committee, which I'll talk about a little bit at the end of the presentation, since 2013. And I'm currently, and I was a member of the Unitary Leadership Council up to 2020, and I just rolled on to the Applied Sector Council. So in DOE, I participated in that 2013 rulemaking. I participated in a 2015 rulemaking. At Aaon, another fellow was kind of taken over the government affairs, but I'm the old hand that knows a bunch of people, so I've been helping him out still. So Kevin Tinkle runs government affairs now for Aaon. So how all these kind of work together now is ASHRAE develops this method of test. HRI develops the listing standards and the metrics. They work with ASHRAE to develop the 90.1 ratings, which are the minimum efficiency standards published by ASHRAE every 3 years. Now, since 2013, the U.S. Department of Energy has federally regulated. So up until 2013, the ASHRAE standards for minimum efficiency included in 90.1 was the standard of care for consulting engineers. But they had no force of law behind them. They were just good recommendations. They were considered, if you got in a lawsuit, you could go in and say, hey, I designed this building to the current standard of care in my engineering practice. I followed standard 90.1, like you'd say you'd followed standard 62 for ventilation or one of the other ASHRAE standards. Since 2019, DOE has had the authority to regulate manufacturers so that we are not allowed under federal law to produce equipment that is lower than the DOE adopted minimum standards. So far, since 2013, when this went into effect, the minimum energy standards adopted by the U.S. Department of Energy has been those listed in 90.1. So, so at this point, when ASHRAE or HRI wants to change a listing standard, we have to go through the whole process with the U.S. Department of Energy and make sure they're on board because this is federal law now. So moving at the speed of ASHRAE is now taking on a whole brand new meeting because now we've got the federal government involved in this. So up until 2013, really the only certification programs that were really running around heavily used in the U.S. were HRI, and most people listed their equipment in HRI. Your local codes may require, because local code officials can do whatever they want to a certain extent, they may require HRI certification, but there was no federal law prior to 2013 that you meet this. The federal law even today cannot, because HRI is an independent trade association. Antitrust laws disallow the U.S. federal government from saying that you have to have HRI certified equipment. However, most manufacturers in the U.S. use HRI as our certifying body, and then they report up to DOE because we've had this 60-year relationship with HRI on how to certify products, and quite frankly, they're a lot better at it. So they know how to run the programs and make it work. So these programs cover, like I said, up to 65,000 BTUs, basically 5 tons. In HRI, they certify EER and SEER currently. And since January of this year, for unitary equipment under 5 tons, it's actually SEER 2. I'll talk about that when we get into the metrics a little bit. They also certify a VAP and water-cooled equipment up to 65,000 BTUs, and they certify that for IEER. And they certify heat pumps up to 65,000, and they certify that they add an additional HSPF, which is a part load heat pump efficiency rating. In 340, 360, we certify products from 65,000 up to 760,000 BTUs. That's about 63 tons of cooling. So there is no certified products or federally regulated products above 63 tons. So any air conditioner above that doesn't have a certification. The reason behind that has to do with how big labs are and how big the lab capacity and how big is big, and the fact that once you get above 63 tons, the market gets much smaller as far as the number of units and the number of dollars of equipment shipped out. But that is where that sets today, and I'm not aware of anybody pushing to move that any higher. They certify water and evap-cooled equipment up to 250,000 BTUs, basically 20 tons, for EER and IER, and they certify heat pumps today up to 20 tons, but they only certify full load COP on larger equipment. And we'll talk a little bit about what's coming up on that. So in 2013, and what DOE typically does when they bring one of these test procedures into federal regulations is they do a copy and paste. So DOE typically copies the test procedures that are laid out in 210, 240, or in 340, 360 into the federal rules of regulations under the federal code of regulations, section 10, subchapter D, parts 430 and 431. So they do a copy and paste. So what really happened in 2013 that got everybody's attention when DOE decided to regulate this is the Enforcement and Compliance Division of DOE at that point in time was about 12 people. There was one professional administrator, basically a bureaucrat, who knows how to get things done in Washington. There was one engineer who had worked about a year for a solar energy company that failed. And then the rest of them were mostly lawyers. So you have lawyers writing technical, transferring technical documents. And being lawyers, they always want to change something, right? So they made a couple of minor changes, and I'll talk about that kind of when we get into the metrics about what they did, but it got everybody's attention. Like for my company in particular, we were going to have to test about 9 trillion units per year. So we were kind of wondering how we were going to do that because they changed a couple of words in the regulation on how they define basic models. So that's where DOE kind of enters into this. So so how do you do this in the US? Well, you can, for manufacturers, and by the way, DOE has no authority to regulate you if you're a building owner, or no authority to regulate you if you're a consulting engineer. They can only regulate manufacturers by EPAC. But as a regulated manufacturer, I have to certify my products every year. Every year, I have to keep current certifications to the U.S. Department of Energy. Most of us certify to HRI standards. And the reason we do that is there is a test procedure and a system set up for doing that. That we've been, like I said, we've been doing for 60 years. And and so there's a test procedure, and any kind of test failure involves an involuntary re-rates, fines, and some other things. With DOE, the test data is available has to be available on demand. DOE also has a listing website, which is basically a copy of the HRI website. Plus, you can, if you wish, self-certified a DOE as a manufacturer. So if you're not a member of HRI, if you're not a member of their certification program, you can get on the DOE website and you can self-certify your listings to them. DOE calls HRI a independent certification organization. VICP and they consider if you're listing with them as an independent as proof of certification. At any point, DOE can demand a unit from inventory, or if it's a built-to-order unit, a unit built for them, and they can test it. The real difference between self-certification and HRI certification is with HRI, you build a certain amount of equipment and send to an independent lab under HRI every year that gets tested. Under DOE, they only test when they think there's a problem. They test on reporting either from the public at large, or they test on. I guarantee you, if I fail a test in HRI, I will get a call from DOE, and they'll be testing me too if I fall below federal minimum standards. So, so about 78 companies worldwide choose to maintain their HRI certification on unitary equipment. So in HRI, we test every year 20% of what we call our basic model groups. All right. And basic model groups are generally defined as compressor capacity plus or minus 5% and a condenser coil square foot area. So in reality, what a basic model group is a tonnage. So a 3-ton unit's a basic model group, a 2-ton unit's a basic model group, a 20-ton unit is a basic model group. And so 20% of all the basic model groups that I as a manufacturers get tested every year at HRI. For units under 20 tons, I build 3 units if I'm a build to order company, or they select 3 units out of my inventory if I'm a distributor based company, and they will sample test one. They'll come in and HRI will pick one of those 3 units and test it. For things above the 20 tons up to 63 tons, you have 3 sets of basic major components, which is 3 sets of coils and 3 sets of compressors. And they'll come in and say, use these compressors and use these coils and build that unit. The reason for that is these are much more expensive units, so it becomes a lot more burdensome to build 3 units for tests that you're never going to sell, basically. So so each sample is tested in an ISO 17025 qualified independent lab. I can tell you there's 3 of those in the U.S. One ran by Underwriters Laboratory in Plano, Texas, and one ran by ETL, Electrical Testing Laboratory, part of Intertech in Plano. They kind of trade techs back and forth. And then there is the original lab was an ETL lab in Cortland, New York, and so they also test in Cortland, New York for HRI. Those are the 3 approved labs that are independent ISO 17025 qualified labs. Those are also exactly the same 3 labs that DOE uses when they test, because they have the same requirements of testing in an independent, non-manufacturer owned 17025 qualified lab. So in HRI, if you fail that test, you get a $10,000 fine, and you re-rate everything in that basic model group. If I fail it by 10%, I re-rate every tonnage, everything that's a 5-ton unit, if I fail the 5-ton unit, down by 10%. So within those basic model groups, you may have 50 different flavors of 5-ton unit. You can have one that's got a 6-row coil or a 2-row coil or a variable speed compressor or a on-off compressor or a 2-step compressor. And if I want to list different efficiency ratings for any of those different combinations, those are different listings within that basic model group. When HRI selects their selection every year, they also randomly select, or, it's their choice. They can pick any of those independent listings at any voltage. I always say they love to pick 575 volt stuff to make sure I can never sell it, because that's only can go be sold to Canada. Or if I introduce a brand new model with some fancy variable speed, typically that will get picked that year. But, in theory, they randomly select within each basic model group which units to test. So you really have to be really good at all your products, have to really understand how all your products work, because failing a test is a really big deal. If that failure, so every year, every day, actually, the HRI listing database gets uploaded to DOE and gets merged into the DOE database. Also, anytime a unit fails HRI and it falls below federal minimum standards, that gets reported immediately to DOE. And so that's one of those places, like I said, where DOE typically will pull a unit and test. So in theory, all your basic sizes get tested at least once every 5 years. In 2019, which is the last time I had budget numbers, HRI testing was about $20,000 or $20 million that for just testing unitary equipment. So there is a lot of money spent by HRI, and that is part of our membership dues. And if you're a member of HRI as a manufacturer, as part of that certification program, we're funding all this testing, and they spent about $20 million in 2019. I'm sure it's more now. So, like I said, the listing test, the metrics listed are EER, SEER, now SEER 2 for single phase, HFPF, and HFPF2 now for single phase, because there was a new rule that went into effect in January of this year. For things above 5 tons, it's EER, IEER, and there's a new metric, IVEC, that's coming in 2019, and a new heat pump metric, which is a part load heat pump metric called IVHE, that's coming in, not in 2019, 2029. So there's a couple of new things coming our way as far as these metrics go. The U.S. Department of Energy, by federal law in EPAC, can only regulate one metric for each class of equipment. So for SEER, for things lower than 5 tons, they used to certify SEER, now they're certifying SEER 2. If it's single phase, and SEER if it's 3 phase, and HFPF for heat pumps if it's 3 phase, and HFPF2 if it's single phase. For equipment bigger than 65,000 BTUs up to the 63 ton level, they certify IER for cooling and COP for heat pumps. So just kind of talking about what, I've been talking about some of these metrics and what they are. So EER is simply the number of BTUs per hour divided by the watt. So it's kind of it's a anglicized COP, if you think of it that way. So it's just the cooling capacity divided by the number of watts. And all the part load metrics, SEER and IER, are weighted averages of EER at different load points. Typically, when you hear EER, if someone says the EER of this unit is X, it's at the full load HRI condition, which is 95, 75 outdoor, 80 degrees, 67 wet bulb indoor. So those conditions are kind of a nationwide average that were developed a number of years ago across the United States. And I always thought it was interesting that the 2 cities that come very close to 95, 75 Outdoor conditions are Atlanta, Georgia, where ASHRAE headquarters is based, and Washington, D.C., where DOE is based. Or that's about their design conditions. So those are the full load conditions. They are, if you just say EER, that's that's full speed on the compressor with full airflow as defined by the manufacturer, and the manufacturer gets to define the airflow at the test condition.
Hey, Mark, could you, I got a question here.
Sure.
Could you review that? So you're saying the airflow is determined by the manufacturer. That's not part of the standard, like a CFM per ton or?
No, it is not. It is not. And I can guarantee it's not 400 CFM per ton.
Okay. And then what about?
So typically those airflows are adjusted to maximize the energy efficiency.
Right. And then the cooling power. So what's included in that? Are you including your fan energy, your
yes,
airflow?
That is the power coming in the power cord into the unit. So
Do
that
you
is the
account
control
for
power.
what if you have things that are consuming energy that have nothing to do with the cooling? Yeah, an electric heating coil, for example.
Well, electric heating coil at 95-75 will likely be off.
Okay, so it's only what's operating.
It's what's operating, so basically we've got a power meter on the power input into the unit. So that's the fan energy, which I'm going to talk about here in a minute. That is the controls, whatever power it's taken to run the controls, whatever power it's taken to run, so.
And your fan energy will be different if you've got, HEPA filters versus 2-inch MERV 8s. So you're rating it when you have the minimum filters, basically?
You're rating it as a minimum filter. So part of the negotiation that happened in 2019 is, there are all kinds of rules you get in the Federal Register, and it'll actually tell you what it is. There's a default filter pressure drop, or you can put a filter pressure drop, but it's like a MERV 11, MERV 8 or MERV 11 filter. It's a fairly low efficiency filter going in there, and it's a fairly simple unit. This is a coil, a fan, a coil, a filter, and a box. So typically for cooling energy, there is not a heater in there. Or there's an electric heater. You're given, there's a little different energy efficiency if you want to include a gas heater, because actually there's a little credit for having the pressure drop across a gas furnace. The other thing that I'm going to talk about here in a minute is the pressures that these units were rated at have traditionally been very low, and that's the reason we're moving to some other metrics like SEER2 and the new metrics for bigger equipment. But we'll get into that here in a second. So,
thank you.
So SEER, I always say somewhere around 80% of the dollar value of equipment sold in the U.S. is under 5 tons. It's completely dominated by residential. So SEER is the most complex metric, but in general, and I'm not going to tell you how to calculate SEER because it's different for different types of equipment. And if you have variable speed compressors, it gets really complicated because you do multiple tests. And if this point is bigger than that point, then you use that point, so there's some logic in here, but basically the tests are run at 95, 82, and 67 outdoor dry bulb temperatures. All the indoor temperatures are always 80 degrees and 67. For cooling, and the highest weighting on a SEER rating is always kind of at that 62 point. So if you're a manufacturer and you're creating a unit and it runs really good I'm not at 62, at 82. It runs really good at 82. That kind of dominates the weighting factors. And like I say, SEER is a lot more complicated than IER, which we'll talk about next, because it's more defined, because there's some logic in here, but the 82 test is the one that dominates that. There is also a cyclic factor, which happens in any time when you have a stage compressor and you cannot meet the load points, or can't, if you can't run your unit constantly at 67 degrees outdoor dry bulb temperature, it needs to cycle at that point, at that load condition, with then you have to include this cyclic factor, and the cyclic factor is 0.2. And what that cyclic factor really is how much energy does it take to turn a compressor off and turn it back on again. And whenever you turn a compressor off, you've got all the water, latent water on the coil, that when you turn it back on tends to re-evaporate and becomes a negative latent load in the space. There's also a certain amount of energy that it just takes to get the refrigerant, get the evaporator cold and the condensing unit hot. And so the default value for that is 20% basically of the energy, running energy of the unit it takes to start it, stop it, and start it again. 20% penalty. And so depending on how many times you have to start and stop it, you have the cyclic factor in there. But it's a 0.2 every time you do it. Now, there's also a test for that cyclic factor in 210, 240, and actually in 242, 340, 360. And my experience is you never quite get to 0.2. The worst I've seen is about 0.18. The best I've seen is about 0.09. It tends to kind of be a random number generator. If you run it 5 times, you kind of get 5 different numbers. They're not, but it's somewhere between 10 and 20% basically is really a true number. And so if you don't want to do the test, the default value is that 0.2. So the heating HFPF is a similar type thing. It's an average EER, weighted average EER at various conditions. The tests are run at 62, 47, 35, 17, and 5. Although 17 and 5 are optional points, you do not have to run them at those outdoor points because you may lock your air source heat pump out, which a number of years ago, many air source heat pumps were locked out at low ambient temperatures. There's a push now to have low ambient heat pumps, and now we're opening that up. So the test is only ran at 75-degree dry bulb indoor air condition, or and a test is run at 75-degree dry bulb. So the indoor condition is 70-degree dry bulb, 60 wet bulb. The weighting is most affected by 47-degree outdoor test. That's kind of the standard rate weighting for heat pumps. And by the way, 47 usually is a test running at 47 degrees. Rarely are you doing defrost, just as a point of information. And there again, you have that cyclic factor. When we get into IER, into the bigger equipment above 5 tons, it's a lot simpler in the fact that it's at 100%, 75%, 50%, and 25% load on the building. And so it's at 100%, it's 95, 74.5. So basically 95, 75 wet bulb. At 75%, it's at 81.5, 73, kind of close to that 82 point I was talking about on SEER. 50%, it's 68, 57, and at 25%, it's 65, 52. Now, if it's air-cooled equipment, then these wet bulbs make very little difference on how it affects the coil. If it was a vac-cooled or water-cooled equipment, then they would matter. So if you look at the weighting factors, at 100%, it's 2% weighting. At 75%, it's 61% weighting. So you can see that 75% point is really the key point. So if you design a piece of equipment that runs its best at 75%, you'll have the highest IER. Now, I've been in a lot of buildings in my lifetime, in my 43 years in the industry, and walked up to a lot of air handlers inside big commercial buildings. And I'd almost bet you on an occupied building, the VFD on that air handler is going to be running somewhere about 75% if it's an occupied building. So I don't feel too bad, since commercial buildings are generally dominated by the interior load. That 75% weighting, that's probably reasonable weighting factor. So that kind of makes sense to me. And, if you size your equipment and you don't oversize your equipment, and you're using, if 95 was your design temperature, your 2% ASHRAE design temperature, then in theory it'd be running 2% of the time, right? So that's kind of where those numbers come from. Now, these are numbers that are used for all equipment across all climates. So there is not a IEER for Denver versus Miami versus New York City versus, Calgary, Canada. So it's this average number, so that they have limited applicability to figuring out what it's actually going to do in your climate, and your mileage may vary based on your application. So for heat pumps on larger equipment, as of today, we just use COP, which is just the heating energy in watts. How many BTUs converted to watts does this create, divided by the heating power? And there again, like I said before, we're measuring the whole power of the unit. That includes the fan energy and everything else. And for heat pumps, of course, the idea is that our COP is greater than 1. We are pumping some heat from the outside, so electric resistance heat, if I had 100 watts of heating, 100 watt of power in produces about 100 watts of power out. With a heat pump, I can get more than 100 watts of power out, depending on how warm it is outside, how much heat I can pump in. So thus why, as we move to electrification, heat pumps are becoming extremely popular. So the efficiency standards in 90.1 changed on January 1st this year. And so the efficiency went up. There's always a step up. And typically these efficiency standards gets reviewed by federal law. DOE has to review them every 3 years. So the 90.1 cycle is every 3 years. Every 3 years we make, we review the energy standards. We decide whether we need to raise them or lower them. I mean, raise them. We can't ever lower them, or leave them the same. And this year, this was a significant jump for most efficiency. And the really significant jump on a lot of equipment was that we could no longer use a single compressor on-off compressor. And I'm not in the residential market, so I haven't gone out looking. I can guarantee you, if you've got on-off compressors, you have a very, very large condensing unit, if you were able to squeak that by. Most of the equipment on the commercial side, most of the stuff I deal with, if we had single compressors, we had to go to 2-step or digital or variable speed to meet the energy levels with a reasonable size condenser. And so what you saw in a lot of builder grade equipment, a lot of the stuff that's designed at minimum efficiency, there was a major redesign. A lot of times the cabinets had to change sizes. The number of stages or number of compressors had to change. So there was a lot of redesign going on this year. So in 2023, we also developed a new metric called SEER2. Now, SEER2 was put into effect by DOE only for single phase equipment, which they call residential. So this really only affects residential equipment. And the SEER2, and I've got a slide coming up here that'll talk about where the stuff is measuring. But the big difference in SEER and SEER2 is we raise the external static on the test units for SEER2 up to 1/2 inch. So one of the dirty little secrets of all this HRI testing, and somebody asked earlier about, is the fan energy in there? Yes, the fan energy is in there, but the static pressures that all these equipment is tested as by the standard and that's been around for a number of years, is extremely low. So these were like, but prior to this, a 5-ton unit was tested at about 2/10 of an inch of external. So we raised it all up to 1/2 an inch. That caused a problem. The reason we haven't done it before now is by EPAC, that law passed in 1975, DOE could never backslide. They could never say a lower efficiency level is acceptable than we previously had. If I put that, 3/10 of an inch extra fan static on there, then it consumed more energy, and we were not able to maintain the same SEER levels. So the SEER levels would have to get worse, which was not allowed by DOE. So the DOE lawyers came up with this brilliant idea of, well, we'll lower the numbers, but the way we're going to lower the numbers, since we can't do that by law, we'll just create a new metric and we'll call it SEER 2. Kind of a lame name for doing that, but really what SEER 2 is a dodge so that we can put more static pressure in the test procedure, get something that's more reasonable to reality of how things are applied. And we've enacted that this year for residential units. The next cycle in 2026, you're most likely going to see that for SEER rated products on 3-phase equipment. So here's the static pressures that are listed in the standards prior, and it was changed for residential to 1/2 an inch, but like I said, that 5-ton unit was at 2/10 of an inch. A 2-ton unit was 1/10 of an inch, and this 63-ton unit that was the top of the certification was a whopping 3/4 of an inch of static pressure. So I'm sure all the consulting engineers out there in the crowd designed all their 63-ton units with 3/4 of an inch of static pressure. Obviously, that is ridiculously too low. So really, when all this was put together way back when, 50, 60 years ago, it was really looking mostly at refrigeration efficiency. It really wasn't looking at airflow efficiencies. So what's happening in these standards now is we're trying to raise them up to more reasonable levels, but they're still not going to be the level you necessarily have on any particular job or design, because we have to pick a number to test to. Because there's only so much test capacity in the world, and there's only so many units we can test per year. The other thing about the DOE SEER 2 and HFPF standards and SEER standards in general is they're regional standards. So the levels are different for the Southeast, the North, and the Southwest. So hot, humid versus cold versus hot, dry climates have 3 different levels that are set. And to make things a little more interesting, the North was based, the ability to sell units were based on the date of manufacture. So if I built a whole bunch of 13 SEER units and stockpiled them in the North, I could have kept selling them past January 1st this year, but I couldn't have sold those in the Southeast or Southwest because it's based on date of install. Now, because of supply chain issues and the fact that no one had anything in stock this year, this really didn't matter. But this is the way those standards have been set up. So if you look at those SEER standards, you got the North, Southeast, Southwest. So for SEER, you had 14 in the North, 15 in the South, in the Southeast, Southwest. So you can see these change a little bit from a manufacturer standpoint. From an Aaon standpoint, I know what we do is we only build equipment to the worst case scenario in any of these, just because we can't manage. We don't want to be managing people bootlegging units from New York down to Florida, where you could have, or vice versa, where I could have a lower efficiency unit and install it in a high efficiency requirement area and crossing state lines. But in theory, if you wanted to build a regional based units, you could have you could sell 14 SEER commercial units in the north, and then you'd have to have better units to sell in the southeast and southwest. Now, I was talking about those really low static pressures. The what's coming in 29, and this has been in the works with a negotiated rulemaking between DOE and ASHRAE and HRI, and basically was completed at the end of last year of what the rules and what the metrics are. There's 2 new metrics coming: the integrated ventilation economizer cooling method and the integrated ventilation heating efficiency method. So for things above 5 tons, there's going to be these 2 new metrics. They're going to be a lot more complex than just 25, 50, 75, and 100. They're going to raise the static pressure requirements up 2 to 3 times on those, but it's also going to account for economizer cycles, integrated with mechanical cooling and how you integrate those. None of that is addressed in the current IER stuff. It also is going to talk about, look at different operating modes, going to look at off mode power. So do you have to run the crankcase heaters and the compressors to keep the oil warm? And do you have to keep the controls running? How much power does that take when the unit is off? All that kind of gets factored into this new metric to give you a more reasonable comparison of 2 different pieces of equipment. If you're just going to say, is this piece of equipment more efficient than that piece of equipment? So since every piece of equipment, this is completely new test procedure and even more complicated than just raising the statics, all the equipment has to be retested, and so there is basically, we're going out a couple of cycles. 2029 is likely the date. DOE has not yet set the exact date of implementation when this will happen, but everybody's working on the fact that this is going to appear in 2029. These new metrics will go into the 2029 version, probably the 2028 version of 90.1, which will come effective January 1st, 2029. So a couple things coming your way, and I didn't actually set on this negotiated rulemaking, so if you asked me exactly how it's calculated, I couldn't tell you. Kevin Tickle from our company did that, but it is going to be more reasonable, although still not something that I can put in an energy model and really get a real good number. So let's kind of talk about, I'm going to kind of change from the regulatory stuff to the practical stuff of how do you actually test a unit. So ASHRAE 27 dictates unitary equipment tested in basically in 2 room psychometric chambers. So you notice there's a 80-67, there's a 95-75 basically test condition. And so typically this equipment is tested in 2 environmental rooms where we have to maintain 80-67 in one room and 95-75 in the other room during that full load test. So these are all steady state tests. They are tested at one point with the equipment completely settled in and running. So it's not a transient test. It's not a test of the control system. It's a test. It's kind of an artificial at this point in time. Once the equipment's warmed up and running and ready to go, what kind of energy is it going to consume at that point? And for rooftop equipment, typically they use over-under chambers. You can use side-by-side chambers, but then of course you have to duct things across. And so this happens to be a picture of one of my chambers in my facility with the outdoor room upstairs and the indoor room downstairs. So the unit's installed in that upper room. You can see a big piece of equipment going into this upper room. Door gets shut. We put sampling trees on the coils, and these will have to cover 80% of the condenser coil area. There's also a sampling tree in the supply and return duct, and this sampling tree runs through a psychrometer. In the lower room, that discharge is ducted into an airflow meter, which is sitting down here underneath that blue structure. So we're measuring mass flow of the air. There again, that sampling tree in that duct has to cover 80% of the discharge and 80% of the return. And the supply and these sampling trees basically feed what we call a psychrometer. Psychrometer is this little box. It has two high precision RTD type temperature sensors. One of those temperature sensors has a cotton sock. You can see toward the back of that picture that goes down into a little pool of distilled water. So in the summer of 2023, the state of the art of measuring moisture content in the air is still a cotton sock on a thermometer. Nothing electronic is as accurate because I can do a very, very accurate temperature measurement with that. The closest thing electronically that the ASHRAE committee that's on 37 that's been working on this has come up with is what I call a chilled mirror, which measures dew point by a solid state cooling chip that chills a metal mirror down to a point where and shines a laser off it with a photocell, and you're looking for the point where condensation begins to form. They cycle about once a minute, so you only get one reading a minute. And once that mirror gets dirty, which it tends to do after a half dozen cycles or so, then the temperatures start drifting off, so the accuracy goes away. Excuse me. So like I said, this is kind of the state of the art today. It has a little fan that pulls from that sampling tree. There's a little airflow meter in there that keeps that 1,000 feet a minute. So it's really nothing more than a sling psychrometer that's automated. And because the length of these tests is an hour per data point, your arm would get really tired if you had to stand in each ductwork with a sling psychrometer. Typically, this is all ran into computer, and for each test, you have to run those rooms and stabilize those rooms so that the sampling coming off those coils or on the supply, return, and condenser coil stay within plus or minus half a degree of wet bulb and dry bulb for that 30 minutes. And then you record for the next 30 minutes. And in my chamber, we record once a second for 30 minutes. So it takes an hour to do a test. It takes about 2 hours to get those rooms stabilized where you can do a test. And so in my lab, we run 12-hour shifts, a really good 12-hour shifts for data points. So, and we're doing this in our lab so that we can determine what numbers to list on our equipment. The HRI testing that they do at ETL and UL, they do exactly the same test procedures in very similar facilities. And, they have, so they can test, basically they can test 1 unit per 12-hour shift. So and then typically it takes a day and a half or 2 days to get a unit in and set up. So, getting 2 or 3 units a week, even if you're running a 24-hour shift like ETL does, is challenging. So there's a limited amount of test capacity in the world and a limited amount of labs, even if you count all the manufacturers' labs that we have available to us. Like I said, if we're doing low temp heat pump testing and we're going to 17 degrees for those heat pumps, it could take 4 hours to get that unit into condition. So so one IER or one SEER calculation in a day is really good, and in reality typically it takes more than a day to do that. So that's kind of how those tests get done. Now, there is no comparison. You can't take a 5-ton unit that has SEER and compare it with a 6-ton unit with IER. Those are apples and oranges with different weighting factors. SEER was developed on the weighting factors on SEER were developed with the idea that the load profile of the building was a residential load profile. meaning that you get up in the morning at 8 o'clock, you go to work. The house is empty during the day. At 5 o'clock, you come home. The internal loads pick up. You cook dinner. You go to bed. So the load profiles and the weighting factors were based on building modeling based on that kind of profile, whereas IER was based on a commercial profile, which is basically the opposite. You come in the building at 8 o'clock during the peak environmental load season or solar load. You're fully occupied, or you're averagely occupied, and then at night you shut off and you go to a minimum setback system. So IER and SEER are slightly different in weightings just because the load profiles that they were looking at the buildings to come up with those weighting factors are different. You also can't compare IER with VRF, which also has an IER, but the IER and the VRF is different. They're different conditions, and typically VRF systems don't account for being able to handle much latent load. They're mostly sensible load units. So the original HRI standard 1230 was basically with a dry coil. Now, DOE wasn't very happy with that, and they're in the process of changing that, and the newer VRF ratings that are coming out now, or shortly. I'm not in the VRF business, so I don't exactly know where we're at on that. We'll have a different rating, but it's kind of unfortunate that we got two metrics named the same that are actually not the same test conditions. Water source heat pumps are different. Number one, water source heat pumps don't have a part load rate metric. They're only full load metrics of EER and COP. Although there's some work going on in DOE, ASHRAE, and HRI about to develop a part load metric. They are using an ISO metric 13256-1. They are all the temperatures are hard metric conversions, so they're a little bit different. And the other thing that ISO 13256-1 does is it actually extracts the fan and pump horsepower out, so it really is only a refrigeration unit. So in fact, if you make a water source heat pump and you put a better than average modeled fan in it, when you extract it out as the average modeled fan in the math, you get a little extra refrigeration efficiency if you use a better fan. So it's a oddball standard. There's a lot of push by energy advocates, by DOE to do something else. The problem that HRI has and the rest of the industry has with ISO 13256 is it is an ISO standard. It was used in Europe at the time it was adopted a number of years ago. It was used in Europe and the US. The Europeans have since kind of changed, and now they're listing their water source heat pumps with their normal heat pump standard modified. And so they no longer use ISO 13256-1. The ISO rules for changing a standard are that every country gets one vote. And because the US is only one country and we're the only people using the standard, we can't get enough votes from the rest of the international committee to form a standards committee to change the standard, which seems really stupid. But so really what's going to happen is HRI and ASHRAE need to go off and develop a new standard that's our own, that's not an ISO standard, so that we can make something more reasonable, maybe more comparable. So kind of a lot of legalese, a lot of regulatory stuff going through here. But kind of going forward, I want to talk a little bit about where I think we need to go. So none of these metrics can you use to put into an energy model and really get any useful information. They're rated at this ideal average weather data on this ideal average building that has very low static pressure right now. and really isn't looking at shoulder season and all the other things that go into it. So you can't really put it in a in an energy modeling program and figure out how many BTUs per square foot per year this building's going to use. And that's really where we need to get to if we want to save energy. Let's see. So going forward, if we really want to say we're going to hit max tech on a lot of this equipment, probably if we're not there in 2029, we're going to be darn close. And what I mean by max tech is we're going to hit the theoretical efficiency of how big a condenser I can put on a certain size compressor and get more efficiency out of it. If you look at water-cooled chillers today, we are basically there. If you look at the best water-cooled chillers out there in the market, they are running 1 degree approach on the condenser, which so 1 degree between the discharge pressure, saturated discharge pressure, and the water temperature coming into that condenser, and then on the evaporator side, 1 degree between the building water leaving water temperature and the saturated suction temperature. If you want to make that 0.5 degree and get more efficiency out of that, you're going to have to put 100 times more copper in there, and you're going to get a few tenths of a % more efficient. So basically, we've just done all we can do under vapor compression refrigeration. So we've done as good as we can do with the equipment. Now, that being said, I don't think we operate our buildings very well. There's lots of opportunity for controls. There's lots of opportunity for energy recovery. There's lots of opportunity for how we control buildings. And because we rate this equipment by a very kind of simplified metric where 75% load means everything, we may not be optimizing that equipment to be optimized across the range it actually operates at. So ASHRAE has a new standard out called ASHRAE 205, which is a performance map for equipment that basically says at any static for, let's say, unitary equipment, at any static pressure, at any airflow, at any outdoor condition, wet bulb and dry bulb, at any indoor wet bulb and dry bulb, I would be able to, within the operating envelope of that equipment that I allow that equipment to operate, I'll be able to interpolate and tell you how many watts it takes to produce that much load at that point. So there's a committee within HRI that we started in 2012. I was one of the charter members, and we're working with all the different sections, all the different equipment manufacturers in HRI to get these rating maps. I can tell you we're not there yet. We really don't know how to do that for rooftop equipment today. The computer modeling isn't quite there yet. The chiller, actually water-cooled chillers, or actually even air-cooled chillers are there, because when you certify a chiller today with HRI, you actually certify the software within its operating range. Now, it has to be plus or minus 5% at the IPLV points, and it can wander off to as much as plus or minus 15% at the edges. But it's still better than not having anything out there, because one of the things that happens as we create these maps are uncertainty. Our ability to predict what it'll operate at all these is because I can't test all these points. There isn't enough time in the world to test every piece of equipment at every operating point. So there's some round off and computer modeling error that takes place. But we've proven with chillers we can get within 15% at the very edges of the envelope. So when you certify a chiller with HRI, you test the IPLV points and they pick a random point, and I guarantee it'll be in some corner. If you say your chiller will operate at 65 degree leaving water temperature at 52 degrees outside air temperature, that's the point it'll try to run at. It'll try to run, they'll test that chiller at that point. So we've got some things going. one of the issues we have today with energy modeling, which goes into net zero buildings and all the things that we're talking about, is that when we actually do all this modeling and then we actually look at the utility bills on these buildings, it's not agreeing very well. And I think that we have a lot better idea of what the building dynamics and the transfer functions and maybe we could get there on occupancy loads and how much people create on the load side, but we don't have very good equipment models. Most of the equipment models in the DOE software or any of the software being used are basically the same models that were in BLAST in 1975. They're very crude equipment models. They don't account for multiple stages. They don't account for variable speed. They don't account for a lot of things. So that's something that I think you're going to see coming up probably the next, 6 to 10 years. And there's a big push in the industry for developing when you hear somebody say we want 205 data, that's what they mean. They want this big 3-dimensional or multi-dimensional map where I can interpolate between these actual map points and say, hey, at any point, at any operating, at any condition, this is what I can have. It's pretty easy with chillers because water doesn't have latent load. When you throw latent load in there and latent coil models, then things get way more complicated, and that's kind of where the system steering committee and the people working on unitary products are stuck at. But that's where we're headed. That's where we're trying to get to. So with that, that's the end of my presentation. I'd be glad to answer any questions anyone had.
All right. Well, Mark, thanks so much for doing this for us, and I hope everybody enjoyed. Look forward to seeing you on the next one.
Okay. Thank you.
Thanks so much, everybody.
Yeah.
Bye-bye.
All right. Thank you.
Bye.